We've got kind of the shell of a sphere. I guess if you can think of it like a hemisphere, I'm going to draw the full sphere out though. So we've got a sphere, it's got a radius of 4a. However, what we've got, our particle, so our particle is actually kind of going in a circle around there. So it's going around in a circle. You can imagine if that's kind of, a hemispherical bowl, something kind of tracking circles around a little bit away down from the rim. We've got 4a or 4a all the way from there to there, but what we've got, so that's the centre of our circle, that distance from there to there is 2a. So the circle is at a distance of 2a below the centre of the sphere. I'll put this in on here, maybe just faintly, but I've got 4a there, and I've got that length of 2a there. And we're not given anything else, are we? That's it. And then just show the speed of the particle. Obviously, we know that we have got the weight there of mg. We have got the force is actually acting in that direction there, isn't it? So the force that's keeping that on the sphere, on the surface of the sphere, is the normal reaction. That's acting towards the centre of the sphere. However, the direction of the acceleration is acting towards the centre of the circle that the particle is going around in. So it is a bit confusing because you've got two different radiuses here, haven't you? You've got two different centres. But this is the one that we're concerned about for our circular motion. We want an angle. We'll call that theta. So I think it is worth here because I've got various different lengths and so forth happening. So I'm going to draw out that triangle there. I've got my angle of theta. I've got a 4a and a 2a. So of course I can work out sine theta. Sine theta, no, it's not sine theta, it's cos theta. Adjacent over hypotenuse, 2a over 4a. The a's had cancelled, 2 over 4 leaves a half. So you might think there, oh, hang on, if cos is a half, I know what this other one's going to be, but we can just work it out using Pythagoras. I've got 4a squared minus 2a squared. That's going to be 16 minus 4, so 12a squared. Square root 12 is 2 root 3. So that's 2 root 3a. So if I work out sine of theta, opposite over hypotenuse, that's going to be 2 root 3a over 4a, and I haven't left enough room there. Sine theta, the a's cancel, that 2 with a 2 within that 4, and we're just left with root 3 over 2. And of course, some of you might have spotted that just anyway. If you've got cos theta equaling a half, then of course it's root 3 over 2, which means that your angle there is going to be 60 degrees. Right, so we have got horizontal circle. Horizontal circle, we always do the same two things. We look at what's going on vertically. Vertically, it is in equilibrium. Going downwards, I've got the weight going up. Okay, well, we've got a component of that r. Shall we try and do it without drawing the diagram again? So if I draw my vertical in there, that angle there is also theta. I've got an alternate angle. If that's theta, the vertical component is adjacent to that, so it's cos. So forces up, r cos theta equals forces down, mg. There are no other forces there happening at all. Cos theta is a half, so a half r equals mg, so r is 2 mg. Now we look at what's going on in the horizontal direction. We're going to be resolving towards the centre of our circle. And of course we're going to use F equals ma, where F is resultant force in the direction of motion. There's only two forces. The mg, the weight, doesn't contribute anything because that's acting perpendicular to our direction of the acceleration. So we've just got the other component of r. It was cos previously, now we're looking at that one. That's opposite the angle, so that's going to be sine. So r sine theta is equal to ma. We've been asked to find the speed, so for a, let's use v squared over r. I have got my r, which I know is 2 mg, sine theta, which is √3 over 2. Mass times by v squared, which is what we have to find, and then we have got r, and r is 2√3a. That 2 cancels with that 2. I've got an m over there and an m over there, so I'm left with √3g on the left equals v squared over 2 √3a there. Multiply both sides by that. 2 √3a times by √3g is v squared. √3 times √3, 3 times by 2 is 6. So I've got 6ag equaling v squared. So v is √6ag. Okay, so there seems like fewer steps, doesn't there, in this one in the previous ones. However, it being algebraic made it a little bit more awkward. And I think, you know, these two different circles and the two kind of different radii just complicated it as well. Okay,